Welcome. My name is Ben Bischel. Welcome to our advanced machine learning lecture here, and welcome to the second part of cost-sensitive learning. So in the first part, we studied what a cost-sensitive ML task is, what a cost matrix is, and how we can define a minimal expected cost principle to turn posterior probabilities, either estimated or true ones, into optimal hard labels, which come with minimal costs, hard label predictions. And we can how to do this also by thresholding on the output of our probabilistic classifier. So here we will turn this theoretical consideration into an empirical algorithm for empirical thresholding, and we will also introduce our first algorithm, which makes our underlying classifier cost sensitive in training. So until here we have only operated on the predictions, and we'll do that by considering the quite well-known model-agnostic MetaCost algorithm that we can put on top of every available classification algorithm to us. Because I guess that's what model-agnostic means. Okay, so let's start with empirical thresholding for the binary case. So we have two classes, and it turns out, we'll also see this in an example later on, that this theoretical threshold from the MECP principle does not always work perfectly, basically because our classifier, the probability, posterior probabilities that it estimates can be biased, will be imperfect, and this also means that thresholding under the assumption that they are perfect is not always best. There's a simple way around this, which is really easy to explain, I guess. So the kind of empirical version of that is not even thinking about what an optimal threshold could be from, I don't know, a priori principles, but just saying, well, if I have my classifier available to me and I can apply this to some form of test data, and then for every threshold I can simply measure the computed misclassification costs, right? So I just take my classifier. In a certain sense, that works like producing an RC curve, right? So how does producing an RC curve work like? You take some data, let's say some test data. We have our probability scores for each observation in the test data set, and now we simply threshold them with a given threshold, and now I would compute the true positive rate and the false positive rate, right? And that gives me 1 point in RC space. What I do here is even simpler. I compute just one metric, and that are the misclassification costs. So I threshold with a given threshold my probabilistic output of my classifier. I get a confusion matrix from that. I compute the misclassification costs based on my given cost matrix C, and now I get 1 point here on that curve, right? And I do this for every threshold, and then I get a pretty fine approximation of this curve here, and I can now simply numerically optimize that. So I can plot that, I can study it, but I can also numerically optimize that, because this is now a one-dimensional simple minimization problem, and I can just empirically compute here where this minimizer is located, and I'll just take that as my optimal threshold. So I guess there are a couple of small comments here in order. So usually we would not do this on training data to avoid overfitting. So usually we would do this on predictions on a validation set, or in general on test observations from resampling. So e.g. cross-validation. So you cross-validate your data and then threshold on that, produce this curve here, and then numerically optimize for the best potential threshold. If there are multiple local minima with either exactly the same costs or nearly the same costs, we could potentially say that we would like to consider the local minimum, which has a wider span, to produce a more robust version, which is hopefully more robust against overfitting or against certain noise that we have in our data, and that this will generalize much better to the underlying distribution. But there is not much more to say. And to this is a really simple algorithm that you can implement yourself just in a few lines of code. I've brought you here a couple of examples also to kind of discuss how well the theoretical threshold might work if we compare this against now our empirical thresholding procedure. So here we've taken the very, very well-known German credit data set. This actually comes with a provided cost matrix. So the task comes with this cost matrix here. So we have a 1 here and a 3 here. And we can now compute the theoretical threshold with our given formula. And that would make us quite conservative in terms of giving out a credit. So we would only give out a credit if the posterior probability of our client being credit worthy, so to speak, is more than 75%. Okay, so we can now compute this empirical threshold. Also, I guess then we have to define what concrete classifier we would use. So I've done this here for 3 different algorithms. So for logistic regression, for gradient boosting, and for random forest. And then what we have plotted here below is this. So in red, you can see the curve that underlies this empirical thresholding procedure. In orange here, you can see the theoretical threshold. And where this lies, of course, the theoretical threshold is always 0.75 because this is what we computed here from this formula. And you can also see the location now of our empirical minimum. And you can see that for logistic regression and for the random forest, probably because their posterior probability estimates are a bit better calibrated, that this actually coincides quite well. So I guess for the random forest, we could debate whether we can get a slight edge by using the empirical version, but for gradient boosting, we're actually quite far off, and using the empirical algorithm might perform much better in practice. Okay, can we also do this in multi-class settings? Answer is yes, this does work. It's maybe not so obvious now what a threshold actually is because there are, well, more than 2 classes that we have to compare. So I guess we also now need multiple thresholds. And there's a very simple trick we can use. So we can actually now say that we have G thresholds. I will call them CK. So C1, C2 until CK. And I will now use my probabilistic output pi1 to pi g for my G classes and rescale this probabilistic output by dividing through my C threshold values. So I divide pi1 by C1 until I end up with pi g, and I divide that by CG. And my predicted class is now going to be the argmax, so the position of the maximal entry in these rescaled scores. So let's check whether that makes sense. So let's assume all of our scores, all of our thresholds, so all of the entries in C would be equal. So for example, they are all 1. Then taking the argmax of these rescaled scores is simply taking the argmax of the posterior probability vector, which is something we would have done anyway if there wouldn't have been any costs. Okay? If you now consider the case of binary classification, and you have a C1 and a C2, and you write that down, and I think that's a good homework exercise, you will figure out that you basically just depends on now the relative size of C1 to C2, but the same thing will happen as in our thresholding in the binary case. So this multi-class version simply generalizes what we are doing in the binary case, and this is really, really easy to see. And how would we now practically solve this? Well, we again have to optimize for our ideal threshold, which gives rise to minimal costs, given that threshold vector now. So for each threshold vector, I can compute the costs. So for each, I have my posterior probability estimates based on my cross-validation folds. I take a certain vector C, I compute the costs. Take a different vector C, compute the costs. And now from all of these potential vectors, I want to pick the one that has minimal costs. So I run numerical optimization on this. This becomes now a little bit tougher to optimize because it's not one-dimensional, it's G-dimensional. And if you think a little bit about it, it's actually G minus one-dimensional because it only depends on these relationships between the costs. So there's like one degree of freedom less. So you could, for example, simply fix one. You could fix C1 or CG to B1, yeah, and then just optimize over all of the other guys. But it's still a G-1 dimensional numerical problem. You have to put some work into solving that, but that can be done. Yeah? And then just take that vector and use that for a cost-optimal thresholding and turning your posterior probabilities into hard labels. I want to conclude now with a nice model-agnostic wrapper technique of influencing the training of our machine learning algorithm and making that cost sensitive. And there's a quite well-known and now older algorithm which is called MetaCost. I guess it's called MetaCost because it's it's this model-agnostic wrapper technique. And it basically works like this. So the idea is to relabel our training observations in the form that they have low expected costs for the relabeled class. And then we apply our classifier to that relabeled data. Okay, so the second stage is basically easy. Just kind of apply our classifier, but we fiddle around with the labels of our training data and change them so that the changed labels actually have these low expected costs. So here is a two-dimensional plot, again, of our German credit data set now in terms of two selected features here. So the duration of the requested credit and the amount of the requested credit. And you can see now how the classes are, that some of them become relabeled. Yeah, so these red guys are actually the new classes after relabeling. And we can see here, I guess can't see that much, but at the very least what you can see is that relabeling from good to bad, so where we have like these red triangles after relabeling, that's a more common thing that happens in the algorithm because of our cost structure, right? So if we labeled somebody as bad, we would decline their credit, and we would be in this case here in terms of an error. Yeah, if we would be in this case here, we would predict somebody of being credit worthy, and then they default, and we lose all of our money. So this is pretty obviously why this relabeling to the bad class occurs more often. But I mean, I guess it's now time to formally describe how the algorithm works. I haven't done that yet. So here's some pseudocode. So let's study the algorithm based on this. It looks a little bit lengthy, but we just try to be quite precise in writing this down. It's actually not very difficult. So what do we have in terms of input? Well, we just have our labeled data, right? So this actually works also quite nicely for multi-class problems. So our yi is one of our G classes. So this is our training data. So the algorithm on the inside will use a bagging operation. So capital B is just the number of our bagging operations, bagging iterations. So that's just a hyperparameter. We will fit a probabilistic classifier. I'll just call that pi of x as always. I guess the specific type of learning algorithm is now an input to MetaCost. And of course, we have our good old friend here, capital C, which is our cost matrix, and we want to respect that now in training. So the first thing we do is we just run bagging capital B times in this part of the code. And there's not much to say. So we just create a couple of bootstrapped versions of our training data set by sampling with repeats until we have n observations again. And now some observations might be in there multiple times, and they will be in bag with a certain number of repetitions. So I don't know, the first observation might be in there 3 times. Second observation might even be in there, 5 times. And then the third observation is not in the bag at all. So it was not sampled at all during this bagging iteration. And then we will call that observation out of bag. So we simply do these capital B bootstrap runs. We create our bootstrap version. I call that here db. I train my classifier on that. I call that pi_b. Okay, that's it. Just put all of that in memory, store it. And now the more interesting part comes, which is the relabeling of our training data. And then the final part is just like, okay, let's fit on the relabeled version. That's again pretty simple, not much to say about this. So how does the relabeling now work? So what we want to do is for each xi, we want to define a new label. I'm now just saying because it's now going to be a loop of all of the observations. I guess I'll leave out the I here when I speak about this. So for each observation x, we want to find a new label y tilde, which is cost minimal. So in order to reduce the chance of overfitting, for each observation, I will now compute the vector of indices, okay, m tilde here, over all of my bootstrap classifiers where this xi is actually out of bag. So I'll consider the first, so I'm now given a certain observation. So let's say we just start with x1, right? And I now want to compute m tilde. And the only thing I will now do is I will check the first bootstrap iteration. Was x1 selected to be in bag in the first bootstrap iteration? Yes, it was. So we'll not put it in m tilde. Was it selected in the second bootstrap iteration? Yes, it's also in bag. So we'll skip it again. Was it in the third bootstrap iteration? Was it in bag? No, it was not. So it was potentially out of bag. No, it was not out of potentially. It was out of bag in the third iteration. It maybe was also out of bag in the fourth one, in the seventh one, and so on. And on average, for me, it's a little bit more complicated, but I guess some might know how large this set is going to be. So on average, this fed set contains about a third, or n divided by 3 elements. Not exactly, but approximately. And this is simply the indices for our first observation, where x1 can consider to be a test observation for all of these associated classifiers. So pi3 never saw x1 in training. pi4 never saw x1 in training. So what I will now do is I will compute an average probability estimate for xi by predicting with all of the out-of-bag classifiers on xi and then simply average their values to kind of get a smooth out-of-bag probability estimate. And if I have that, I will now simply apply my MECP principle that we discussed before. So I will simply compute the cost minimal class when I pretend that these smoothed out probability estimates here for that class are actually the true posterior probabilities. And I'll now create a relabeled version of my training data set, and I will run my original classifier on this with these changed labels. And it turns out that this can work quite well. This will make the classifier respect the costs in training and give rise to smaller costs, when we would test that, for example, in cross-validation or on test data. Okay, this brings us to the end of this section here. And the next section will discuss instance-specific costs and how we can perform cost-sensitive learning on such more complicated and general tasks.